So this is EE698G, lecture 12. So I'd like to quickly start with where we stopped in the previous class. Any questions on this? So your question was, if it advances, if you have a small signal step here, what happens to the time domain signal? Is that your question?
Will it advance from exactly, I mean the drop in reference T will be occur at exactly that point where the small signal is rising?
So let's assume that in the absence of any small signal, you had the ideal square wave like this, right? Now the small signal step is happening at this point, right? Now at this point, even if the signal advances, because it is a square wave, you will not see anything at the output, correct? So a nice way to think about this is, you would expect to see these rising and falling edges, assuming we are dealing with a 50% duty cycle square wave. You would expect to see these happening whenever your total phase crosses 2 pi. So whenever it crosses multiples of 2 pi, you see a rising edge. When it crosses odd multiples of pi, you expect to see a falling edge. Right? So I would urge you to go back and think in terms of the definition we used here, right? Where you are thinking about a sine wave that is being passed through a comparator. If the sine wave value is positive, comparator is giving you VDD. If the sine wave value is negative, comparator is giving you 0. So imagine that you are obtaining the square wave by taking a sine wave and passing it through a comparator, right? So wherever the sine wave is crossing a 0, you have a rising or a falling edge corresponding to that, right? Now you put the total phase inside the sine wave, find out if it is crossing a 0, if it's positive or negative, and then translate that in terms of the square wave. Yes.
When we are saying that there's a small signal phase, there's a step in that. So that basically means that in the time period of the reference signal is going from Tref to Tref plus delta T.
Is the time period changing?
Because there's a new...
So time period, right? You would relate it to the frequency of the system, right? And frequency is the slope of the phase.
What is the amount
of... So it's just getting shifted?
Few edges are getting shifted, right?
But the total time taken for one period is the same.
So you might see a different time period in this particular period alone.
Yeah. So
because one or two edges are getting shifted. So
that will be lesser than what Tref?
If an edge is advancing, then it will be lesser than Tref. Right? But the rest of the time periods are not.
What is the amount of edge that is advancing? Can we calculate it?
Yes, of course. So let's say this was some delta phi.
Okay, from there, right?
Right? If you know what is delta phi, you are now in a position to calculate what is delta t corresponding to that. So with this, you would be able to calculate whether the edge is, by how much the edge is shifting. Now in this particular case, you can see that all the edges that will happen after this instance, you can see that the total phase of the signal has now increased. Phase increasing means that the signal is advancing, right? Which means all of the edges that happen after this instance is going to move towards the left, right? And the phase has simply increased by a constant delta phi. So all of them are going to shift by the same amount.
The delta phi is larger, then instead of falling edge, you will encounter rising edge immediately. There.
If the delta phi is larger, okay.
To be at the position of the falling edge. Instead of falling edge, you will get a rising edge.
So again, I would think, so you are talking about certain corner cases, right? One, the assumption is these are small signals, meaning the phase difference is very small. Right? But even if we were to take the scenario that you are asking about, let's say this was the original sine wave. Now the scenario you are saying is suddenly there is a, let's say I'm taking here, there is a sudden phase jump, right? And how much do you want this to jump by? Like at what point, let's say this was some plus VDD, here you have 0 and this was minus VDD, where do you want me to place it?
This is negative, another negative.
You want it to be placed at some other negative value. So let's say somewhere here. So if you are getting it here, then the signal will look like this. Right? And then you simply use this as a threshold and get the square wave. Yes.
Okay, cool.
Yeah.
So then the second falling edge of reference T.
So let me number the edges. So this is 1, 2, 3, 4, 5, 6, 7, 8. Edge number?
Edge number 4.
4.
Come at T reference plus delta 1, right?
You're asking what the position would be?
Fourth position will be at T reference plus delta 1.
It will be T reference minus delta 1. Signal has. So let's say this was 0. This position was 0, right? This position is T ref. This is 2 T ref. You would have expected it to happen at 2 T ref earlier. Now it is 2 T ref minus some delta.
That fifth edge, right?
The fifth edge. So the fourth edge is basically
2 minus that.
1.5 T ref minus some delta. Is that okay? Any other questions on this? Okay, so let's quickly complete the right side of the plot, because as you saw, this is part of the question paper. How would we already, out of T simply is a delayed version of reference of T, right? So all the edges, as they appear at the reference, have to get delayed by one more T ref, right? We have already plotted how the phi out of T's large signal picture is going to look like, right? So the total phi out of T, the total phase at the output will look like this, because that is simply total phi ref of T delayed by T ref, which means the small signal. So if this was T ref, originally you had the step happening at T ref plus delta 1, which means now you will have it happening with a delay of 2 T ref plus delta 1. So it is 2 T ref plus delta 1, and your signal is going to rise here. Okay? This is clear? Now, I also want to stress on how the type of notations we have used. Your large signal is being represented by capital phi with capital subscripts. Is capital subscripts. Small signal is small phi, small subscript. And finally, the total signal is capital phi, small subscripts. The convention we generally follow for analog signals. So if there are no other questions, let's quickly do the quiz. So let's continue with the lecture. So we have been trying to model a VCDL unit. This VCDL has two inputs. We have a reference signal, which is a voltage domain signal. But of course, we are interested in the phase of the signal. Right? We also have a control voltage, Vc as a function of time. And then we have out of T, and again we are interested in the phase of this output signal. Right? So there are two paths, and we said we will deal with one path at a time, and we have been currently looking at the path from reference to the output. So in analyzing this, we have kept our Vc a constant such that the delay of the VCDL is our operating point delay, which is T ref. Right? We saw how the waveforms have come out. Let us quickly see if we are able to derive this from the equation. So out of T is simply reference of T minus T ref. We are going to represent out of t as some function of its total phase. Right? So what should I write here? Some function.
Phi of ref
Is it phi ref of t?
minus
Should be t minus t ref. Right? So which means I can directly start looking at the phase relationship.
this will be minus 2 by right? With the phi of t minus 2.
If we are looking only at the large signal, right? So now I can split this into a large signal component and a small signal component. So this is phi out of t plus a small signal phi out of t. This will be equal to a large signal component delayed by t ref plus a small signal component delayed by t ref. So far okay? So can you quickly tell me the expression for phi ref of t, the total phase of reference minus the total phase of the output?
2 pi.
Is it 2 pi?
Small things.
Yes.
So you should get
9.
phi ref of t minus phi out of t plus a small signal phi ref of t minus a small signal phi out of t,
Same.
right? Where this expression is now equal to 2 pi. Okay. So for the case we were discussing in class yesterday, can you quickly sketch how phi ref of t minus phi out of t is going to look like? So,
This is to subtract the individual term and then plot.
so the plot I want is this. Phi ref of t minus phi out of t. This is on the y axis. X axis is time. Etc. How does it look like? Is it constant? So the DC point, the operating point would have been a constant 2 pi, right? At t ref plus delta 1, your phi ref of t has a step, right? Phi out of t has a step at 2 t ref plus delta 1. So you would see that at t ref plus delta 1, you have a step, and because phi out of t also sees a step at 2 t ref plus delta 1, it comes down. So the total signal will now look like this. This is okay? Summation of both.
The straight line should be a bit high, right? Because that is 2 pi and that is delta.
This is, of course, it's a qualitative diagram, but it's a very valid point. So you're saying that this should be a small step, right? Yeah. That is correct. So this value is 2 pi. Okay. So now let's start looking at the other path. So we now want to model what happens to the output. So this is ref, output of t. Now we are going to assume that we have some VC, which is a function of time. Corresponding to that, the VCDL delay is some delay which is also a function of time. Okay. Now the expression for out of t will be equal to reference of t minus this delay, which is a function of time. Very interesting problem to have, right? So let us get to the basics and look at the VCDL characteristic. We will assume that a current starved inverter based characteristic is being used, which means we are looking at a curve like this. Right? So this is your TP and this is your VC. Now to analyze this, we will assume that the small signal phase occurring at the input is 0. Right? You have a very clean square wave coming at the input. Now this VC can be written as an operating point phase. So this is the small c, capital C as a function of time, plus a small signal VC as a function of time. Now under steady state, we would expect our operating point to be a constant on an average. Right? You could have some ripples around it, but every period the average of VC is going to be constant. And in doing our continuous time model, we are interested in that average behavior. So this is not a function of time anymore. Right? And because capital C and small c can be difficult to differentiate, I'll simply add a 0 here. So VC operating point. Okay. So now at VC operating point, what do you expect the delay to be? That delay is going to be Trf. Okay. So now I want to write an equation for the delay Tp as a function of Vc. But this curve, as you can see, is very nonlinear. And we want to be able to work with linear systems at small signal level because that makes our life much easier. Right? So we are going to linearize this curve around the operating point. To do that, I will draw a line through this operating point where the slope of this line will be same as the slope of the curve at that point. Okay? So I draw a straight line. This happened to nicely touch here. Let's say this point is some T naught. Right? What is the slope of this line? This is going to be KDL. Right? I'm going to represent an S here to show that this KDL is being represented in seconds per volt. Right? So can you tell me the expression for TP? A y-intercept is given, you know the slope, you know the variable on the y-axis, you know the variable on the x-axis. This is going to be KDL VC plus T naught, right, where KDL is negative. So KDL S. So far okay? So now I can write it as T naught plus KDLS. I'm going to split this into the operating point plus the small signal VC. So this is equal to T naught plus KDLS into VC naught plus KDLS into VC. Can you tell me what this parameter is? This should be equal to Trf, right? This is equal to Trf plus KDLS into Vc. So far okay? So now let's look at something interesting. Let's say I want to calculate this. If this Vc was dependent on time, my delay Tp is also a function of time. So Tp of t is equal to Trf plus KDLS plus Vc of t. Now here is the thing. If I have to define a delay, the next edge has to appear at the output. So if this is my VCDL, let's say I gave an edge here, right? I can define the delay or I can measure the delay only after the next edge has appeared at the output. So let's say the VC changed at the same instant as the signal is entering, right? Only after this edge has appeared at the output, I'll be able to measure the delay, right? So you see the effect of change in VC after the edge has appeared at the output.
So in that duration, the VC can change a lot of times.
It could potentially change a lot of times, right? So even if I write VC, it is VC of t minus after some duration, right? Any comments on what this duration should be? Any approximate value you can give? Plus?
Less than T1.
It has to be lesser than Tref. Assuming Tref was a nominal delay, this edge, once it enters, can take up to Tref to come. It will be closer to Tref. Right? Any change you are making is expected to be a smaller variation around the nominal delay of Tref. Right? So writing it as it can be lesser than Tref.
It can be greater than Tref also, right?
It can be greater than Tref by a small amount. Right? So a good approximation to make is to say that this is T minus Tref. This, of course, we are making an approximation, right? But this is a reasonable approximation to make when you are working with the first level model for the DL. Okay. So now we have an expression for TP also. We have figured out how the VCDL can be modeled as we go from one input to the output and the other input to the output. Let us put both of them together. So the equation we'll work with is the very simple equation of out of t being equal to ref of t minus Tp of t. Right? So I can write the total phase phi out of t as equal to the total phase phi ref of t minus Tp of t. Okay. So the phi ref, this is a total phase. Let me quickly split this into the large signal phase. Plus the small signal phase. So far okay? Now what comment can you make about the large signal phase? So if I were dealing with a very nice square wave, how would the large signal phase look like? You know this. It is linear. What would be the expression? So this is going to be some omega ref into time. Right? So I'm going to replace that here. So this is omega ref into the time, where the time is now t minus Tp of t. And this component appears as it is. Okay. You already know what is the expression of Tp of t. Right?
This expression Tp of t is the total delay or the
Tp of t is the total delay.
like
Right?
Tref plus delta t.
Tref plus some delta t. We are still writing the total phase. Right? So we'll write the total phase on both sides, and then we'll bring out the large signal components, small signal components, and analyze them. So in this expression, you technically know everything. Why don't you give it a try to simplify this? Let's see what you get. So now what is the expression for Tp of t? This is some Tref plus KDL in seconds per volt into Vc of t minus Tref. Right? So I will substitute that. So you get omega ref into t minus omega ref into Tref minus omega ref into KDL in seconds per volt into Vc of t minus Tref. This plus phi ref of the argument is t minus Tref minus KDLS into Vc into t minus Tref. Now let's try and simplify this a little bit, right? So the first term omega ref into Tref appears as it is. What can you comment about this? This becomes 2 pi. Any simplification you can make here? This becomes KDL in radians per volt, right? So what you have is some KDL in seconds per volt that you are multiplying with omega ref. Basically it is getting multiplied with 2 pi by T naught. So dimensionally this is KDL in radians per volt, which I'll write as KDLR, right? So one minor thing you have to remember is if your delay is increasing, what is happening to the phase? Phase is decreasing. Delay increases, phase decreases. The relationship is opposite, right? If the phase has increased, which means the delay has reduced because the signal is advancing, right? So minus KDL in seconds per volt into omega rf gives you KDLR. So I can replace this whole thing with KDL in radians per volt. Okay? So this is 2 pi plus KDLR into Vc of t minus Tref.
T naught is also included.
Sorry?
T naught is also included to convert into radians.
So it is omega ref into KDLS. Negative of that will give you KDLR. So it should be 2 pi by Trf. Did I write T naught? Yeah, it is 2 pi by Trf. Okay. So you have a VCDL, right? It has some delay. If your KDL is positive, what does that mean? When your VC increases, delay is increasing, right? Now for a signal, if the signal has been delayed, what happens to the phase? Phase is decreasing. So when VC increases, phase is decreasing. So if I want to represent that relationship, the slope has to be of the opposite side. That's all. Right. So we have one more term here. So that let me write as phi ref of t minus Tref. I'm going to call the remaining delay as some time t1. Okay. Now, can we quickly identify what is acting as a large signal or the operating point and what is acting as a small signal here?
First two terms are large signal.
Right? This is your large signal, capital phi out of t. Right? The remaining two terms are small signal. This term is coming because of a change in Vc. This is the small signal phase at the input getting delayed by whatever is the delay of the VCDL. Right? So you have two terms. Now this whole portion is your small signal phi out of t. Okay. Quickly tell me, between Tref and T1, which of these terms do you expect to dominate? Tref and T1. So T1 is KDLS into Vc, the small signal Vc. Tref is expected to dominate, right? So we will simply assume that this second term can be simplified as some phi ref into T minus Tref. Okay. Now I can show you what sort of error this assumption is going to introduce. There are two terms in our small signal phi out, right? Let me call this as phi 1 and let me call the second term as phi 2. So if your small signal phi ref, let's say, is going high like this, right? Let's say it is going high at some instant tx. And I want to plot the small signal phi out. I'm going to assume some shape for phi 1, right? And phi 2, ideally where would you expect this to happen? If this occurred at tx, here it will happen at tx plus tref plus t1, right? So you would expect to see a step here. So the total signal phi out will follow this curve, then you will see a step here, then it will follow the rest of the curve. Right? Now all that I am assuming is, instead of this happening at Tx plus Tref plus T1, it is happening at Tx plus Tref. Right? And this T1 is expected to be very, very small, so this is actually very close. So now your new waveform will look like this. So you make a small error. We are losing out on a little bit of accuracy, but the model we get to work with is much simpler, easy for hand calculations, and this is quite sufficient for first level calculations of the analysis of the DLL. This is okay? So now we are in a position to write the expression for small signal phi out of t. This is equal to some KDL R into Vc of t minus Tref plus a small signal phi ref, which is also delayed by Tref. Let's quickly take the Laplace of this. So phi out of S is equal to KDL R is a constant. This into Vc of S into e power minus st ref plus phi ref of S into e power minus st ref. Right? I can take e power minus st ref outside. So this is KDL R into Vc of S plus phi ref of S into e power minus st ref. We can quickly sketch how the model is going to look like. So you have one input, phi ref of S. To this, I need to add Vc of S scaled by KDLR. So both of these are added together, and then this is delayed by a delay of Tref. This gives you phi out of S. So this is your model for the VCDL. Take a minute,
Don't they
see
think
if you...
those are negative feedback is out, phi out of S and VCDL. Think?
What should we do?
Okay, both are fine. Isn't this VCS dependent again on phi out of S?
Once you put it in the loop. Right now we are only working with the VCDL model. Right? We have not put everything in the loop yet. So,
what are the advantages of making this model?
So this is a feedback loop, right? We want to be able to analyze if the loop is stable, right? We want to be able to say what is the transfer function from input to output. If there is noise somewhere in the loop, what is the noise transfer function? So we want to have very quantitative ways to analyze all of these properties of the loop, right? Because right now we are working with rough idea. If I increase the charge pump current, I know that the loop is likely to lock faster. But by how much faster is it going to lock, right? We are engineers. We want to be able to give quantitative numbers for everything, right? So that is the aim. Like theoretical analysis of DLL, which will help us design a better DLL. So take a minute, feel free to discuss, see if you have any questions on this model. Let's quickly revise what all approximations we have made. So the first approximation is we have linearized the non-linear VCDL characteristic around the operating point, right? Which means this model is valid only for small VC. If you take a very large, if you have a large change in VC, let's say you end up somewhere here, which means you will have to consider a different line for linearizing. So you will consider a line that is passing through this point with the slope corresponding to that. So you will have a different T0 dash and a different value for KDLS. Right?
So in this case, the operating point will change.
Operating point has to change. So the model is valid for small variations of VC around the operating point. Another small assumption we made was that whenever you make a change in VC, it is reflected in the output after one reference period. And finally, we have ignored this T1 during the calculation for the model. Right? So you will see in a little bit of time that all of these changes, all of these small changes are okay with the assumption we started with, where the settling time of the DLL is much larger than the reference period. Right? Okay, so now what else is there to model? VCDL is modeled. What else is there?
Phase detector.
So we are going to model all of the remaining components together. So we are going to model for PFD plus charge pump plus the capacitor. So you have the PFD. There is reference as a function of time, out as a function of time. This is controlling a charge pump. For now, let's assume that both the currents are equal and is equal to ICP. And we have a loop filter capacitor. Right? So corresponding to the phase difference between reference and output, we know that at the end you will have some operating point VC plus potentially a small signal VC of t. Right? Now we want to be able to relate how this phi error seen here relates to the small signal VC of t. Okay? So first step is to calculate what is the phase difference between reference and the output as seen by the PFD. So I am taking the difference of the total phase. What do you see at the output? We calculated this some time back.
2 pi plus.
Right? So this is going to be 2 pi plus small signal phase in the reference minus small signal phase in the output. Now in this, what is the signal to which PFD is responding? Is the PFD responding to this constant 2 pi? No, right? PFD is detecting only the small signal phi ref of t minus phi out of t. So this is the phi error of t for the PFD, the small signal model. Right? Now let's see how to relate this to VC of t. So you have phi error.
Responding to 2 pi. What was the...
Why it is not responding to 2 pi? So if this is your signal, right, and this is the output, let me call this as signal 1, edge 1, 2, 3. What is the phase difference that the PFD is measuring? Where do you want this to log to?
Why should that log to this third one?
Third one, right? So this is the error that it is measuring.
2 pi.
Right? So under steady state conditions, you would have this here, right? So you will have some 2 pi plus an error, where that error can be positive or negative. Is that clear? Okay. So phi error of t. Do you remember the PFD gain? Feel free to go back and check your notes. What did you calculate as the PFD gain? Delta VC? Right. So what is the expression? We calculated gains for a lot of phase detectors. What was it for the PFD? Check your notes. Right? I don't expect you to remember it by. This was equal to VDD by 2 pi? Into phi error. Yeah. So the gain is VDD by 2 pi. Now you got VDD there. Because your up and down signals were swinging between 0 to VDD, right? And then you took up minus down and the average of that. So what should I replace it with now? Instead of voltage signal swinging from 0 to VDD, you are now looking at current waveforms from the charge pump, right? The current switching from 0 to ICP and flowing into the capacitor is what is helping you calculate the average of the PFD, average of up minus down, right? So instead of this, you will have ICP, right? The average current flowing into the capacitor in every period is going to be phi error seen at the input into ICP by 2 pi.
Dimension is not correct.
Because its equation is not complete, right? So this is the average current flowing into the capacitor. You have the current flowing into the capacitor. How do I calculate the voltage? 1 by C. If I want the voltage at instant t, I integrate it from 0 to t. Right? Let me take all the constants outside. So I have ICP by 2 pi C integral 0 to t phi error of t dt. So this is my Vc of t. So far okay? Let's take the Laplace transform. Vc of s is equal to ICP by 2 pi c into, this is phi error of s divided by s. So I generally like to bring the terms in the order in which the components are present. So you first have the PFD and the charge pump. Together they have a gain of ICP by 2 pi, and this average current is flowing into the capacitor 1 by SC into phi error of S. Now I can sketch the model for this. First let us generate the phi error of S. So small signal phase in the reference. I have to subtract small signal phase in the output from this. This gives you phi error of S, right? And then this goes through ICP by 2 pi into 1 by SC. This gives you the small signal voltage Vc of S. Okay? So you have model of PFD, charge pump, capacitor and the VCDL. Please build the model for the DLL. So now we are looking at the small signal phase domain model for the DLL. So you have phi ref of S. So from this you subtract phi out of S. This gives you phi error of S. Gets multiplied by ICP by 2 pi into 1 by SC. This generates Vc of S, which then is KDL R, and it gets added to this into e power minus st ref, and this is your phi out of S. And I close the loop like this. Okay? So now your signal is taking some time to go from this point to this point, correct? But given that this loop is settling very, very slowly, right? What comment can you make about this delay? The delay from this point to this point. You know that the loop is going to settle very, very slowly. Right? It is going to settle in several TRFs, not one TRF, right? It is the settling time of the loop is much, much larger compared to TRF, right? So there is a TRF delay somewhere in the loop. Given that anyways all signals are going to settle very slowly, I can ignore this delay, right?
Which delay?
This delay.
How can we take it?
So there is a very small delay in this loop.
Yeah.
Right? I am interested in seeing how the phi out of t is varying in a global, on an average, right, over a long time. And settling time.
Big graph and
Okay,
Yeah.
so you are like e to the power minus s TRF, that delay is very, very less than the settling time. So we can
Correct. So we can ignore it, right? So we are saying your loop is going to go like this, right? There is a small delay, every step it is on an average it is following like this, right? Now this delay is very, very small compared to the settling time of the loop. That means I can ignore this. Okay? So this is also removed. Now you have a very nice loop, very similar to the other feedback loops that you have seen.
To any small signal variations, will the loop settle in time very, very greater than t?
Correct.
To any small signal variations.
To any small signal variation, the loop is going to respond to that variation very slowly compared to TRF. Because even if there is a variation occurring, every TRF is when it is going to detect it. And every TRF, it is going to correct for it by a small step.
To design is correct for a small step.
Correct.
But that is an issue, right? If there are errors, like if the fire up is fluctuating so much, so it has to respond to that delay, respond to that change, and it's responding very slowly.
So if the so again, this loop will, as we will see, will have a certain transfer function, and it turns out to be a low pass transfer function. So if your fire F is changing very fast, then your loop will not be able to respond to it.
Yeah, so that is an issue, right?
So if again, so I'll come to that in a minute. The small signal fire F.
The fluctuation that the system should be able to respond to that quickly so that it's able to rectify the error.
So if your small signal fire F was changing very fast and you wanted your system to respond very fast,
Or like it's not changing that fast, but the response should be fast so that it's able to rectify the error.
again, if there's a very high frequency variation in your small signal, right, then you should technically choose your TRF such that you are able to detect it, because your PFT can detect it only every TRF. Now if variation of fire F is happening much faster than what it can detect in one TRF, that itself is a problem, right?
No, like if the small signal variation is fine, but the loop is, for example, it's not changing that fast, but the loop is responding to that slow change also very slowly.
Right. Remember this question, ask me after a few classes, right? Because we are still developing the model and learning about it. So the question that I want all of you to remember is, if the small signal change happening in fire F is very fast, right? It is fluctuating a lot, how can we make our loop respond to it? Right? Because right now we are working with the assumption that the response time of the loop is very large.
In the red curve that you draw, it was the curve of BC settling to BC1.
Right. Because that is easier to imagine, right? A voltage settling from one value to the next.
In that same curve, you told that it captures like that voltage varies in steps. If we focus on that transient parts, it will be linear.
Why would it be linear?
Because the capacitors are charging linearly.
So if I focus on only the VC voltage, you are focusing on only this part, right? This part is linear, I agree. But in the overall image, this will not be linear, right? It is not like the curve is going to go like this to the next value. Right? Okay, so we have a nice feedback loop in front of us. Anytime we see a loop like this, what is our first reaction? break the loop, find out the loop transfer function, right? So please calculate the loop transfer function. So to calculate that, I have to de-energize any independent sources. So what is the independent source here? Phi-ref. So de-energize it. So it goes to 0. You remove the effect of phi-ref. So this gets connected to 0. Identify the feedback loop. So the loop is like this, right? And you break somewhere in the loop. Let's say I break here. I give a phi test voltage. Can you calculate what is the phi out you see here? Phi test, you have a negative sign here
Minus of all this multiplication.
into ICP by 2 pi C KDL R into 1 by S is equal to your phi out. Therefore, phi out of S by phi test of S is basically all these quantities. So ICP KDL R by 2 pi C into 1 by S with a negative sign. Negative sign is coming because this is a negative feedback. This is equal to minus L of S.
We take minus phi return become minus phi return upon phi test.
That's what we are doing. Right? So phi out of S by phi test of S, I have written it as minus L of S. Phi return is same as phi out in this case. Right? So you now have a very nice expression for L of S given by ICP KDL R by 2 pi C into 1 by S. I can calculate the magnitude of L of S as magnitude of L of j omega. This gives you ICP KDL R by 2 pi C. I want you to remember this into 1 by omega. $1 million question. What is omega here? Yes, frequency of what?
It's a
Feel free to discuss before you answer.
small frequencies.
Sine disease, which we converted into sine waveform.
Frequency of the sine?
No.
There is no sine as such in the loop variable.
The phase is fixed around a point, and it's like
That's a variable.
it's varying about the
So variation of what?
phase itself.
Variation of the phase.
Yeah.
So variation of the small signal phase. Is that okay? Right? Okay. So I want to let's take a time to understand this. Right? So this omega is basically talking about the variation in the small signal phase or the frequency of the small signal phase. Right? So let's quickly go through few cases to understand this better. I'll use a reference case to start with. Assume an ideal square wave, right? In which case my large signal phase, is simply a line like this. Right? Now I'm going to add different small signal phase to it and see its effect in the output. We have already seen what happens if you give a step. So this is your large signal phase plus if I add a small step to this, you know how it is going to behave now, right? All the edges are going to get advanced. Now, instead of a small step like this, let me assume a small signal phase which is varying very slowly. Okay? Can you tell me how your total phase is going to look like and how the reference is going to behave? How would the total phase look like? So this is the operating point phase, same as a large signal phase. How would the total phase look like? It's going to go like this, right? So if your original square wave looked like this, right? How would the new square wave look like? All of the edges are going to advance, right? Because at all points the phase is higher. The edges happening around this period would have advanced more, right? So this would advance by a larger quantity, but all of them are going to advance in this direction. So your new square wave is going to look like this. Okay. Now, as a homework, I want you to consider the scenario when your small signal phase is a negative value, let's say like this. Right? And your small signal phase has large variations, something like this. So sketch the total phase and figure out how your square wave edges are going to shift.
When the small signal phase was above the x-axis, that's why the modified phase is always higher than.
Correct. So the small signal phase this is some delta phi, right? And at all instants, this delta phi is greater than 0. So I have to sum up both. If delta phi was 0, you would have been here on this line, right? So that plus this new curve. Right, you will have delay. So you have a small variation in your phi ref. How are the edges delayed? But just plotted one so that you are familiar. So now you should be in a position where you see a small signal phase, you should be able to imagine how the voltage domain waveform is changing corresponding to that. Right? Yeah. Thank you.